All right. Welcome to the preparation of aspirin lab. This lab has two goals. The first of which is to teach you basic percent yield calculations. The second goal is to introduce you to functional groups. So let's get started. Let's take a look at the reaction that we'll be conducting. In this lab, we'll be reacting salicylic acid with acetic anhydride to yield aspirin plus acetic acid. Now, if you look at the book, you'll notice that this equation is written using a series of figures. And we really want to get into what those figures look like. First of all, for salicylic acid, you'll notice you have a hexagon. I can draw a neater hexagon than that. You have a hexagon with a circle inside of it. Then you've got an oxygen hydrogen sticking out here. You have a carbon double bonded here. And you have an oxygen there. What in the world is that? What in the world are they telling us with this weird looking figure? What's the deal with that hexagon with a circle inside of it? This lab is really your introduction to organic chemistry. Organic chemistry is not the study of life. Rather, it's the study of compounds that contain carbon. Now, all life as we know it in the universe is based on carbon-containing molecules, and biochemistry is really an outgrowth of organic chemistry. But all life contains carbon, and therefore organic chemistry is a very important, very big field. However, a lot of the compounds we look at when it comes to compounds that contain carbon are really, really large. A lot of the compounds organic chemists look at are really, really large compounds and aren't really practical to draw a full-fledged Lewis structure that we look at. Let's look at one that's a little bit borderline just for conversational purposes. Let's say we have the compound C6H14. Well, if we drew the Lewis structure of it, the way we have been drawing the Lewis structure of compounds in class, that's how we'd write it. Now, it's big, it's huge, it's inconvenient, it takes up a lot of room. Imagine what we'd have to do if we were going to draw something that's 25 carbons long, right? Not only that, but it took a lot of time and effort, and we still don't really have a lot of information about structure. And additionally, it doesn't really convey what's going on. We can come up with a different type of notation to allow us to rapidly draw carbon and hydrogen containing compounds that's faster, easier, and actually really provides a little bit of information in terms of the three-dimensional shape of this object. And that's the stick notation. I can draw a stick. Let me just draw this compound this other way, and then we'll talk about it. Whoops. Okay. And now I lost count. Let's see, 1, 2, 3, 4, 5, 6. All right, I've drawn a series of lines, and you're saying, Dr. Kelly, that series of lines just looks like a big squiggle and doesn't look anything like the Lewis structure here. So how can this squiggle that I just drew represent this compound? In organic chemistry, when you're using line notation, like this, each end of the line represents a carbon atom. Each end of the line represents a carbon atom. So when I write this, what I'm saying is that I have a carbon here, a carbon there, a carbon there, a carbon there, a carbon there. Not only that, but when you're using line notation, it's assumed you don't want to draw all those hydrogens, so it's assumed you have as many hydrogens as are needed. So not only do my ends of my lines represent carbons, but each one of those carbons is going to have as many hydrogens as is needed to complete the Lewis structure. Let me see if I can't make that a little bit neater for you. So even though I didn't write my hydrogens in, it's assumed I have as many hydrogens as needed to give each carbon 4 bonds. Right? Carbon wants 4 bonds, so you're going to have as many hydrogens as are needed . That means your terminal carbons here and here would wind up with 3 hydrogens, and the carbons in the middle would wind up with 2. All right, let's see how well you're understanding me. Write down the word Scotty. Write down the word Scotty. S-C-O-T-T-Y, Scotty. All right. Take a look at the structure I'm showing you here. Give me the formula for the compound represented by this structure, and also write the Lewis structure for it. Please pause the video and try this on your own, because guess what you're going to be seeing on the quiz, and if I give you a midterm, the midterm and the final. All right, hopefully you paused me. I know you paused me. Who can resist pausing me? All right, So first thing we need to do is we need to count our carbons, right? So we've got a carbon here, a carbon there, a carbon there, a carbon there. So I have 4 carbons. Next I need to deal with my hydrogens. I know each carbon is going to have enough hydrogens to have 4 bonds. This carbon only has 1 bond it's participating in, so it gets 3 hydrogens. This carbon's participating in 2 bonds, right? A bond here and a bond here. So it gets 2 hydrogens. Same for this carbon, is participating in 2 bonds. This carbon here at the end is only participating in 1 bond, so it gets 3 carbons. So we have a total of 10 hydrogens. I said carbons right there when I should have said hydrogens, obviously. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. And there's this Lewis structure, by the way. Alright, quick thing I didn't address. People are probably wondering, hey, when we draw the line structure, why are we drawing things at angles like this? Remember from lecture that carbon's a tetrahedral, right? So if you have a tetrahedral, let's focus on this terminal carbon here, you're going to have bonds at angles like that, right? So when we draw this zigzag pattern in carbon, we're also representing the fact that carbon likes to form that tetrahedral structure, creating those little bond angles there. Alright, so that's a pretty simplistic example. Let's kick it up a notch. What do we do if we have a compound that has a double bond? Let's take a look at a really simple example of a compound with a double bond. Alright, we're looking at this compound, and this compound, for the record, would be C3H6. How would we draw the line structure for this? Well, we have 3 carbons, right? 1, 2 carbons, 3 carbons. How do we represent that we have a double bond? We represent a double bond in our line structures simply by drawing a second small line right on top there. And that's how we would represent a double bond, simply by drawing that simple line there. Alright, let's take a look at a compound, this time not with a double bond, but with a triple bond. And let's make this compound a little bit more interesting. Here we have the compound C4. H6. If we want to draw the line structure for this, we're going to need to draw our lines. Just start out counting our carbons. 1, 2, 3, 4. Right, carbon here. 1, 2, 3, 4. One thing that you can always check yourself is Note, you're going to have one less line than you have carbons. Okay, so how are we going to draw this? Well, remember, if we drew a double line, we just drew one extra line. For our triple bond, we're going to draw two extra lines. So this triple bond occurs between our second and our third carbon. There's our second carbon, there's our third carbon, so we're going to place our triple bond right here by drawing a line above and a line below. So there's our triple bond there in our structure. So that's how you'd handle a triple bond. Let's take a look at a structure now where we have a compound, not a compound, an element other than carbon making up part of the molecule. Let's say we have this molecule. Notice how I'm not naming these. There's actually a systematic way of naming all these, but I'm going to leave that for organic chemistry. Matter of fact, most of what you'll do in organic chemistry, not a most, but 25% of your time will actually be spent in organic chemistry learning how to name things. All right, now. What you do is when you have a substance, an element other than oxygen in your Lewis structure or in your structure, you draw your sticks like you normally would, but then you place in that element. For example, I really have 1, 2, 3, 4, 5 elements in sequence here, right? So I'm going to draw 4 lines. Let me count, make sure I didn't mess up. 1, 2, 3, 4, 5. Yeah, because I have 5 elements in sequence. 1, 2, 3, 4, 5. My oxygen is my second element in my chain. So what I'm going to do here is I'm going to go over to where I have this chain, and I'm just going to draw in my oxygen. Right? So my chain, just to make it a little bit less messy, would look like this. And that's how I'd represent that compound. Chemistry's easy, life is hard, yes? Alright, let's say I made this compound a little bit more interesting, and I changed one of my hydrogens up here into another group here. Let's say I added a nitrogen. A nitrogen with 3 hydrogens. What I would do is see how that nitrogen there, that nitrogen's not part of the main family here, yes? That nitrogen's only connected to one carbon instead of being connected to the main group here. So what I would do is I'd locate the carbon in the main group that nitrogen's attached to, and that's the fourth thing in the chain, right? 1, 2, 3, 4. 1, 2, 3, 4. That's where the nitrogen is. So I draw a line sticking out of that carbon to my nitrogen. And here, by convention, I would show that the nitrogen's attached to 3 hydrogens. So that's how I would represent it. I would only put the oxygen in the chain, just to be totally clear, if it's connected to 2 carbons. For example, let's look at another quick example. Let's take a look at this compound here. Let's not do it that way. I'm sorry, I don't want to make things too confusing. Alright, if we look at this compound here, we have one oxygen that's part of the chain, one oxygen that's not part of the chain, right? This oxygen is only connected to one carbon, whereas this oxygen is attached to two. Oh, and let's make this a little bit even more interesting. Let's add down here, because this is one of the things that we will be looking at in this class. Now let's just work this example. All right, I've got 1, 2, 3, 4, 5, 6 carbons or oxygens making up my chain. So I need to draw 5 lines. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, my oxygen's my third thing in it. So I'm replacing that carbon, or that corner, with an oxygen. So now I have 1, 2 carbons, then my oxygen, then 1, 2, 3 more carbons. This next to last carbon, as I've drawn it, has an alcohol group, or an oxygen, with a hydrogen attached. So I'm drawing that. And there's my structure. Ta-da! Now let's give you one to try. Draw the stick structure for this. Pause me. Please pause me. Do, 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 do. Did you pause me? I know you paused me. All right. If we look at this, we have 1, 2, 3, 4, 5 things in a chain. So we need to draw 4 lines. 1, 2, 3, 4. Our third carbon is our third corner in our line is an oxygen. So we're going to replace that corner with an oxygen. Then we have one other thing to pencil in here. We have an oxygen double bonded to our second carbon. Since that oxygen isn't part of a chain, what we do is we draw 2 lines to represent that double bond, and then we have an oxygen attached. There you go. Write down Sulu. Write down Sulu. S-U-L-U. Sulu. All right, we started this conversation by talking about salicylic acid. And it seemed like we kind of got sidetracked in an attempt to explain what in the world this hexagon was with a circle in it. Well, now, thanks to our discussion of a stick structure, we have a little bit of a clue now. We know that everywhere we have a line being joined in this structure here, that means we have to have a carbon, right? So that must mean I have a carbon, a carbon, a carbon, a carbon, a carbon, a carbon, and a carbon. So I wind up having 6 carbons forming this hexagonal circle. What about the circle? Why do I have this circle here? Well, remember we said that when you have a double bond, you draw a second line. Turns out that when you have 6 carbons double bonded to each other in sequence like this, you have a potential resonance situation, right? After all, chemically, there's no difference between that and that. So what you do, indeed, fact, have is a resonance situation. And whenever you have a resonance structure, technically you're supposed to be drawing both structures, right? Remember this from our Lewis structures lecture. Well, we don't want to spend the time all the time to draw that resonance. So when we have these double bonds that are rotating constantly inside this circular pattern, we simplify the shortcut. We simplify that resonance structure by saying, hey, the double bonds are rotating, so I'm just going to draw a circle. Now, this carbon circle that we've drawn with the chemical formula C6H6 has a very special name, and it's really important in organic chemistry and biochemistry, and it's benzene. Among other things, it's flat. If we were to look at its 3D structure, it's flat. Chemists love to play with benzene. It's something that we really understand the chemistry of, and we're trying to alter it all the time. When we alter, so what we have here is when we look at the salic acid, we have a benzene molecule at the heart of our structure. So that's one thing. We now know what we're looking at. When we look at our salic acid, we have a benzene structure, C6H6, with double bonds that are in resonance with each other. All right, let me draw our salic acid again here. So in our salic acid, we have a benzene ring, and to that benzene ring, we've added two little outliers here, right? We've got this little outlier here, and we've got this little outlier here. These are what are known as functional groups. What is a functional group? A functional group is a group of atoms that help determine the properties of a larger compound. Functional group is a group of atoms that help determine the properties of a larger compound. They're also a group of atoms usually found together They're also a group of atoms found together in several different compounds. In other words, if we look at our salic acid molecule, these two little branches we see right here are both examples of functional groups. An oxygen atom attached to a hydrogen atom is referred to as an alcohol group. Is known as the alcohol functional group. The other functional group we see here is this carbon double bonded to a oxygen hydrogen group, and this is referred to as a carboxylic acid. And carboxylic acids actually contain another type of functional group here. Let's start a clean slide here and look at the functional groups that I'm holding you responsible for knowing. So the first functional group you're responsible for knowing is OH, is an alcohol. Then carboxylic acid group. Then the other groups we want to add are known as esters, like the book of the Bible. They're a lot like a carboxyl group, but you have rest of the molecule. When we see an R in organic chemistry, it means rest of molecule. The part we don't care about. Carbon double bonded oxygen, carbon bonded to the oxygen, and then that oxygen bonded to the rest of the molecule. So when you see that pattern, you have an ester. And let me look at your structures here. What else do we have? Then we also have an acetic acid. Well, no, that's, I'm trying to see what else we have in this. That's it in terms of the functional groups that you're going to be using in this particular lab. Although I want to throw some more in here. Let's take a look at least two more. All right, another one where we have a rest of molecule. Then we have a oxygen and a rest of molecule. In other words, we have an oxygen dropped in the middle of a bunch of carbon. You could almost think of it as carbon, oxygen, carbon. We have that, and that is referred to as a ether, as opposed to an ester. That's an ether. Then, when we have a rest of molecule, carbon double bonded to an oxygen, bonded to the rest of molecule, that is referred to as a ketone. And let's get one more squeezed in here if we can. One more squeezed in here last. Let's do an aldehyde. There we have rest of molecule. We have a carbon, again double bonded, but instead of being bonded to the rest of the molecule or an oxygen, is bonded to a hydrogen. We refer to that as an aldehyde. You need to memorize these groups and to be able to recognize these on any test or in any larger molecule I would give you. For example, Let's take a look at our aspirin. If we look at our aspirin molecule, what we're trying to make in today's lab, if we look at this aspirin molecule, what you'll notice is we've got this functional group right here. That's benzene. Then we've got another functional group, our carboxylic acid functional group. Then, if you look here, we have an oxygen attached to a carbon that's double bonded to an oxygen. Our biblical functional group, our ester. So those are examples of what I'd expect you to do. I'd expect me to be able to draw a molecule and you to be able to identify the functional groups that you see in that molecule. Understanding functional groups and changing them and understanding the chemistry of the functional groups really helps you explain the chemistry of larger molecules. And it helps you understand what's going on in reactions that we're conducting. For example, if we look at the reaction that we're doing in today's lab, we're wanting to make the aspirin molecule that you see here. We're starting off our synthesis with salicylic acid. And salicylic acid, salicylic acid has this structure. What's the difference between the two structures? Well, if we look at salicylic acid, it has an alcohol group. That alcohol group is missing on aspirin. Right? So when we go from salicylic acid, to make it into aspirin, what are we doing? We're replacing the alcohol group with an ester, right? We're basically keeping that molecule the same and just replacing one of those functional groups. All right, let's take a look at, and that's basically why functional groups are important, right? Because even if you didn't know what aspirin was and salicylic acid was, as a chemist, you could look at an unknown compound. Starting over again, you could look at an unknown compound, and if you could identify the functional groups, you could figure out how to transform that compound into another compound because you know the chemistry of those functional groups. A lot of what you'll do in organic chemistry is you'll spend a lot of time memorizing all the different reactions that alcohol groups can undergo. You'll memorize all the different types of reactions esters can undergo. And you'll go to tests and you'll see a test problem that will say, tell me how to convert an alcohol functional group into an ester functional group. And that's really what you're building for. But right now I'm more interested in identification of what we have. All right, now is probably a really good time for you to write down McCoy. Everybody write down McCoy. All right, let's take a look at a couple examples of molecules here. All right. Take a look at these molecules, pause me, and real quickly see if you can identify the functional group in each one of these molecules. All right, did you pause me? All right, first of all, functional group right there, we have a oxygen and it's double bonded to a carbon. Whenever we see that happening, it's a ketone. Here, we have a oxygen double bonded to a carbon, right? There's a carbon there with an OH group attached. Whenever we have that, it's a carboxylic acid. Down here, we have an oxygen in the middle of our stick chain. So we would refer to that as a ether. Up here, we have a carbon, double bonded oxygen, oxygen, rest of group. That's our biblical one. I don't know how familiar you are with the book of Esther, but remember Esther was trying to keep the Jewish people and I believe it was the Persian people happy, so she was having to balance two oxygens against each other. What can I say? That's how I remember it. So that's Esther. Then here you have a oxygen double bonded to a carbon, right? The carbon's not showing, but it's understood to be there. And then it always has enough hydrogen so that it has 4 bonds. So we have an oxygen double bonded to a carbon and 1 hydrogen. And whenever we have that, we have an aldehyde, right? The best grocery store in the world. Aldehyde. Because they hide all the produce. Aldehyde. That's it for this section of the welcome lecture. Why don't you write down chapel before we leave? Chapel. C-H-A-P-L.